Okay, welcome back. So we'll continue talking about satellite motion in the context of gravitational fields. All right, so here's your dot point again. Right, mainly we're just going to be using this formula here to work through our problems. Okay, and we'll see a few different situations that can pop up and different types of questions that can be asked. Mainly though, they're just plug in and use calculator to solve. Okay, there's not too much sort of deep thinking that you need to do, but we'll look at one question where you've got to sort of analyze three responses. This is an exam question. Analyze three responses and sort of just pick which one makes sense or is true and why it's true, and yeah, we'll see. Okay, so here's our first question for this part. So it says, determine the orbital speed of the moon, assuming it's in circular orbit of radius 384,000 kilometers around the Earth. Take the mass of the Earth to be 5.97 times 10 to the 24 kilos. Okay, cool. All right, so strategy here, basically just write down what you know and what you're trying to find. So we're trying to determine the orbital speed of the moon. So that's what we want. Okay, V. What do we know? We know that its orbital radius is 384,000 kilometers. So R, whoa. Okay, R is equal to, let's turn that into meters. So that would be 384,000 times another 1,000 for meters. All right, what else do we know? We know the mass of the Earth. So we know the mass of the central body that is being orbited. Okay, that's what you use in your equations. That's 5.97 times 10 to the 24. And obviously we know big G. All right, so we don't really know anything else. Is this enough for us to work out V? Well, let's go and think about what our main equation is. So we can have G equals Gm on R squared, which is equal to 4 pi squared over T squared. I think there's an R there as well. Equals V squared on R equals A. Okay, that was the sort of mega equation that we found in the last video. That should be written down in your notes somewhere. All right, so all we've got to do is pick two out of these five expressions and pick the ones that got all our variables in them. So that looks like it's going to be that one and that one. There we go. So we've got Gm on R squared equals V squared on R. Cool. All right, so we're basically just going to use this equation to solve for V. Notice we can cancel out this R with one of the R's here. Okay, because if I would just multiply that R across, there'd be an R on top that would just cancel with the one on the bottom. So really it's V squared equals Gm on R. And so V equals square root of Gm on R. Cool. Now that's actually a really interesting formula because look at that, okay? That's giving us a way to calculate the orbital speed of something that's orbiting this sort of main body, in this case the moon orbiting the Earth. But nowhere in this equation does it ask for you to input the mass of the moon, okay? This m here is the mass of the Earth. So the only thing that the orbital speed sort of depends on is the mass of the central body and how far away you are from the central body. So it doesn't matter if you're the moon, which has a mass of God knows what, something huge, or if you're just this tiny little satellite, man-made satellite. If you're at the same sort of orbital radius, if you're at the same location as the moon, your orbital speed is going to be the same. Doesn't matter how big or small you are. Okay, everyone's equal, and isn't that lovely? All right, so let's calculate this. 6.67 times 10 to the negative 11 times 5.97. What the hell is that? Times 10 to the 24 over, what's that? 384,000,000. Why does that keep happening? All right, chuck all that on your calculator. You end up getting something around 1,018 meters per second. Okay, just make sure when you're using this particular equation, like always, make sure your mass is in kilograms, make sure radius is in meters, and everything should be fine. Okay, so yeah, again, make sure this is somewhere on your cheat sheet, somewhere down in your written notes, because that's what you're going to be using when we're doing all these satellite motion questions. Okay, so write down what you know, write down what you need to find, and select 2 out of these 5 equations from up here to work out your question. All right, moving on. So, when we talked about Kepler's third law, we said that this ratio of orbital characteristics for any particular group of satellites orbiting some central thing, that ratio is going to be the same for all of those satellites. Okay, originally Kepler framed it in terms of planets orbiting the sun, and he specified the units of R should be in astronomical units and T should be in Earth years. Okay, so the ratio always turned out to be 1. If you just put it in normal units, so if you just say R is in meters, T is in seconds, then this applies for any satellite orbiting any central body. Okay, and what the ratio actually turns out to be equal to if you use SI units is GM over 4 pi squared. Okay, Newton sort of came up with this. We can do the same thing. We can come up with this ourselves. And the way that we're going to do that is we're going to use this and this and make them equal to each other and just rewrite it in this form. So how would you do that? Well, we've got GM over R squared equals R cubed divided by, what am I doing? Wrong one. 4 pi squared R, that's better, T squared. All right, so notice what I can do is I can bring this R squared, put it on top of that fraction. All right, so you'll end up getting GM equals 4 pi squared R cubed over T squared, and you could probably see the last step involved here is to just divide 4 pi squared across to there, and you end up with that. All right, so that's where that relationship comes from. It just involved a little bit of maths. Okay. All right. So that's pretty much it. Okay. When we use this relationship, if you need to use that at all, I mean, you would have known that anyway if you were to use them based on this setup of 5 expressions, just to use SI units. Okay. There will be one exception, which we'll talk about in the next video, where you won't have to use SI units. But for now, if you're using this formula, put everything in SI units. Just remember, R is in meters, T is the orbital period in seconds, and this M is the mass of the central body. Okay, the mass of the thing that the satellite is orbiting, not the mass of the satellite. All right, so let's do an exam question. So this is from 2017, the first proper exam of this study design. All right, so we've got a whole bunch of data for Pluto and for its moon Charon. And question A says, calculate the gravitational field strength at the surface of Pluto, show your working, and include an appropriate unit. Okay, so this isn't really a satellite question or a orbital question. It is just saying work out little g at the surface of Pluto. Okay, so we've got to go back and think about how we can do that. Well, to work out field strength, you just use GM over R squared. Question is, what is R? Well, if you're at the surface of Pluto and Pluto is a uniform sphere, then R is just the radius of Pluto, right? So we can just pop all of that stuff in. M is the mass of Pluto, which in the data is 1.3 times 10 to the 22 over the radius of Pluto, because we're standing at the surface. Just remember to square this. Okay, don't make that mistake and not square this R value. All right, and you end up getting something on the order of 0.6. And it does ask to include an appropriate unit. Because it's talking about gravitational field strength, you use the gravitational field strength units, which is newtons per kilogram. Of course, this is equivalent with meters per second squared, just we're talking about field strength, not acceleration, so you just use that unit instead. Okay, so that should be a little bit of a refresher on how to work out field strengths at certain distances. So go back and review that video if that was a little bit confusing. All right, part B says calculate the period of orbit of Charon. Show your working. All right, so what equation can we use? Well, go back, look at your mega equation that you've written for yourself. We're being asked to find the period. We're being asked to find t. Okay. Let's see what data we've been given. Write down what we know. So we're being asked to find t. We know the mass of the thing that Charon is orbiting. That is the mass of Pluto, which is 1.3 times 10 to the 22. Do we know its orbital radius? Yes, we do. That's just there. So we know r. It's 1.8 times 10 to the 7 meters. And obviously we know big G. And we don't really need anything else. Okay, it does give us the mass of Charon. But notice when we use this equation, you don't use the mass of the satellite. You only use the mass of the central thing. Okay, so we've got T, big M, R, and G. Which ones can we use to work this out? Well, that one and that one again. Or if you like, you can use the rearranged form and use this. Okay, because that again just only has G, M, R, and T. Cool. So let's actually write it in this way. Okay, r cubed over t squared equals gm over 4 pi squared. So r cubed over t squared equals gm over 4 pi squared. We're being asked to find t, so you can do your algebra yourself. I'm not going to show you how to rearrange this. You end up with t equals the square root of 4 pi squared r cubed over gm. All right. And again, just put your numbers in. Now that you've got a nice little equation to use, put your numbers in. Just be careful on your calculator. Maybe put your denominator in brackets so you don't accidentally multiply it by the mass. Make sure that you've cubed r, not squared r. Make sure you've squared pi and just not left it as pi. All right, just be really careful when you're putting things into your calculator. What you should end up with is something around 5.2 times 10 to the 5 seconds. Cool. All right, 3-mark question. So let's try and distribute the marks. Even this one over here was a 3-mark question. That doesn't really make sense. I don't know. I don't know why this one's 3 marks. I'd only give it 2. Maybe 1 for the writing the formula, 1 for inputting, 1 for the unit. That's probably what it is. This one, 3 marks. No idea. Maybe just writing the formula, rearranging the formula, and I don't know, getting the right answer. Who knows? I don't know what the breakdown of marks for that would be. But there you go. All right. Part C. Now, this is the one where you've got to evaluate responses, which we talked about at the start of the video. Scientists wish to place a spacecraft of mass 1,000 kilograms in an orbit of the same radius as Charon. Okay, so what that's going to look like, here's Pluto in the middle, here's Charon, slightly smaller, going around in a circular path roughly. They want to put a satellite sort of at the same distance. Okay, so they're sort of orbiting in this same circle. All right. 3 students, Rick, Melissa, and Nam, are discussing the situation and have different opinions. Rick says, as the spacecraft is lighter, it will have to move at a greater speed than Charon to achieve the same orbit. Okay, sure. Melissa says the spacecraft would need to move at the same speed as Charon. And Nam says the spacecraft would need only to move at a lower speed as it is lighter than Charon. I could see why someone would think that one. I don't really see why someone might say the first one, unless they think that because it's lighter, gravity is going to, I don't know, pull it down towards Pluto more than it would for Charon? I don't know. The actual correct answer is Melissa. Okay, Melissa says the spacecraft would need to move at the same speed as Charon, and we've got to sort of prove that or give reasons why we think that's the case. And it's as simple as this. If you go back a couple of questions where we worked out the orbital speed, we saw that the orbital speed only depends on the distance at which you are, r, from the central mass, m. Okay, it doesn't say anything about the mass of the actual thing that is orbiting. Okay, it's only the mass of the central body and the distance you are from it. Okay, now because this spacecraft is going to be at the same orbital radius as Charon, they're at the same distance, so r hasn't changed. They're still orbiting the same thing, Pluto, so mass hasn't changed. So that means the speed is going to be the same. There you go. Okay, so you say Melissa is correct because v equals square root of gm on r. It does not depend on the mass of the satellite. Therefore, the other two responses are incorrect. There you go. That's your 3 marks. All right. That I was going to do working out there, but I didn't need to. And we'll stop there. Okay, so go and review the video. Make sure you understand where those responses came from for the exam question. Maybe go and look at the examiner's report. And I will see you in the last video for gravitational fields. Bye-bye.